Hey everybody, here is the solution for quiz number 3 on July 13th. So number 1, we have a CRT TV, or cathode ray tube TV, with a beam current of 10 microamps, or 10 times 10 to the minus 6 amps, or sometimes you could write that as 1.00 times 10 to the minus 5 amps. And for part A, we want to find out how much charge strikes the screen in a single scan. So we know on a CRT TV, at least on US standards, which is called NTSC, the electron beam scans down the entire screen 60 times per second. So the screen is refreshed 60 times per second. So 60 hertz. And we know that the current delivered to the screen is 10 microamps. Well, 10 microamps is equal to 10 microcoulombs per second. So to find the current delivered to the screen in 1 second, we need to divide this current by 60, because it hits the screen 60 times per second. So Q for 1 scan is going to be 10 times 10 to the minus 6 coulombs per second divided by 60 times per second. So that gives us a charge of striking the screen in 1 scan of 1.67 times 10 to the minus 7 coulombs. Or you could also write that as 167 nanocoulombs. So that's part A. Part B, how many electrons is this? Well, we know that the charge on 1 electron is just, well, the magnitude is the fundamental charge. Ten 1.602 times 10 to the negative 19 coulombs. So we can divide the charge delivered in 1 scan by the charge on an electron to get the number of electrons. You'll note I'm leaving out the negative sign on E here, and that's because we just need an absolute value, essentially. We don't need to worry about the signs here, and I'm going to leave it out, just so I don't get something weird like a negative number of electrons. So the charge is 167 nanocoulombs. And the charge on a single electron is 1.602 times 10 to the negative 19 coulombs. So the number of electrons striking the screen in 1 scan, you expect that to be a big number, and it is. It's about 1.04 times 10 to the 12 electrons. Or in other words, about 1 trillion electrons in every scan. That's a large number. And finally, for part C, I'm going to move this over and start a new page. Part C, average voltage driving the electrons on a CRT display is 27.0 kilovolts. So the voltage of the cathode ray tube, that is the potential difference that the electrons are accelerated through until they strike the screen, is 27 kilovolts, or 27,000 volts. And so if we assume that the electrons are accelerated from rest, then all of this voltage will go into accelerating them. So let's see. The energy delivered to the screen by 1 electron is going to be the charge on the electron times the potential difference that it's accelerated through. So that's going to be 1.602 times 10 to the negative 19 coulombs times the potential difference of 27,000 volts. So as you might expect, that's a pretty small number. 4.33 times 10 to the minus 15 joules. And actually, when we deal with energy scales on atomic and or energy values on atomic and subatomic scales, we often use a different kind of measure for energy. A common unit of energy on this scale is called the electron volt. That's denoted by EV, and that stands for electron volt. So 1 electron volt, and you'll recognize the number, is 1.602 times 10 to the negative 19 joules. In fact, 1 electron volt represents the kinetic energy gained by an electron being accelerated through a potential difference of 1 volt. So electron volts aren't compatible with meters or seconds or coulombs or things like that. So if you're doing something like this calculation, you're going to get out your answer in joules. I may ask you to give the final answer in electron volts, but you're going to stick with joules for actual calculations. At any rate, this is the energy delivered to the screen by a single electron. And we want to find out how much energy is delivered to the screen by a single scan, which is just a hair over 1 trillion electrons. So energy delivered is going to be the kinetic energy delivered by 1 electron times the number of electrons delivered. So that's going to be, let's see, 1.04 times 10 to the 12 electrons times the energy of 1 electron, which is going to be 4.33 times 10 to the minus 15 joules. All right, so in 1 scan, we get about 0.00450 joules, or you could call that 4.50 millijoules. All right, so that's number 1. All right, for number 2, let's see, we have a wire carrying a current of 20 amps. And we have a potential difference of 120 volts. And so we want to find what is the resistance of that wire. All right, so we use, for part A, we'll use Ohm's law. And Ohm's law tells us that V equals IR. And we can solve for R. R is going to be V over I. So then we get 120 volts divided by 20 amps. Now we find that the resistance of the wire is going to be 6 ohms. And for part B, let's see. If we want 14 gauge copper wire to have this resistance, how long should it be? So 14 gauge wire has a radius of 0.814 millimeters. And I'm going to write that like this. And copper has a resistivity of 16.78 nanocoulomb meters. Or I'm sorry, nano-ohm meters. And I'll rewrite that as this. Now we know that the resistance of a material, or of some wire with cross-sectional area A, made of material with resistivity rho and with length L, is this. Rho L over A. So what do we have? We know resistance, we know radius, which means we can get area, and we know the resistivity of the copper wire, which means we can solve for L. So I'm actually going to substitute in pi r squared for A, because we're assuming a cylindrical wire, so its cross-section is going to be a circle. And remember, the area of a circle is pi r squared. So let's see, we have rho L over pi r squared. And we want to find L. We know everything else. We know its radius, we know what pi is, we know the resistivity of copper, but we don't know its length. So let's solve for length. L is going to be pi r squared times the resistance, which we already found to be 6 ohms, divided by the resistivity rho. So let's substitute in. We got pi, we have a radius of 0.814 millimeters, so 0.814 times 10 to the minus 3 meters. We're going to square that, times the resistance we calculated from part A, which is 6 ohms. Sorry if I'm impinging on my previous writing. I'm going to try and draw around that. And then we divide by our resistivity of copper, 1.678 times 10 to the minus 8 ohm meters. So plugging everything in, and let me just calculate this out. We find that the length of the wire is going to be 744 meters. All right, that's it.